Okay, in this video I want to go through the Chapter 5 material in this test review. Chapter 5 is dealing with radiation, radioactive equations, etc. So first off, let's look at, we'll use this first question to talk about the different types of radiation that was discussed in the chapter, as well as type of shielding. The best way to protect yourself in the laboratory from these different types of radiation. And the type of radiation is dependent upon the property of the radiation. Right, we had alpha particles, gamma rays, and then beta particles as well. Alpha particles, they're really big. They're a helium nucleus, so in the context of radiation, they're enormous. And so an alpha particle can be blocked basically with like heavy clothing, like a lab coat or gloves. I'll have more to say about it in a minute. Gamma ray, so this is a type of electromagnetic radiation, no mass, all energy, high energy, and so this has a tendency to penetrate the most. And so you require really dense samples like lead or 6 inches of concrete. Now for the beta particle, it's a high energy electron, so it's much smaller than the alpha particle, and so you need something a little bit more dense. Really the best way, most practical way to protect yourself from a beta particle is a 1/2 inch plexiglass in the laboratory. And typically if you're using 1/2 inch plexiglass, that's going to stop an alpha particle as well. So it does dual duty there for you. Very convenient. And then we found, 3 different ways to describe radiation. 1, activity, meaning like how hot is the sample, how much radiation is actually being emitted from a source. There's 2 different unit sets. There's Becquerel for the SI system, and then for the common unit we use Curie. Now just because something has a high activity doesn't mean that it's necessarily dangerous, especially if you protect yourself the right way from it, either by limiting your time, etc. The dangerous part comes in like when you absorb a certain amount of the radiation. So there's a separate unit for absorbed dose. Let me separate the two, SI first and then the common unit. And those 2 units are the gray and the rad. Gray for the SI unit, and then rad is for common unit. And then the final type of unit, or final set of units, deal with the biological damage that occurs for a given type of radiation based on how much one has absorbed. And the 2 units there for the SI unit, it's the sievert, abbreviated SV, and then the common unit is REM, R-E-M. So this next problem is a math problem. It's a dosage calculation problem. We're always given a couple of pieces of data. One, the mass of the patient, and then how much, what is the dose of that particular type of radiation. It's always in activity per body mass. And for this particular unit, we want microcurie, and as it turns out, that's the symbol for micro, and that's the unit that's within the dose. It actually simplifies the calculation. And all we're going to do is we've got to multiply the 2 together, and let's just take a look at how that appears in a dimensional analysis form. So we have the 8.1 microcurie per 1 kilogram body mass, and notice that the reason why this works is because by multiplying the 2 together, kilograms divided by kilograms get canceled out. And so the dimensional analysis is sort of really telling us that we're doing the math correctly when we wind up with just our 1 unit of interest, which in this case, if we do the calculation, we get 688.5 microcurie. Now for this particular problem, there's 2 sig figs there, there's 2 sig figs there. If we want to round this off to 2 sig figs, which we do, then what that means is that we're going to be rounding the 8 to that 8 to 9, and then dropping the rest. Now, since that 0 there is not significant, really the proper way to do this is to put it in scientific notation. So that gets rid of any kind of uncertainty with respect to the significance of that 0. That's it. Last two topics are here. First one, probably one of the more important topics from the chapter, all those different disintegration reactions or emission reactions, decay reactions. Remember, there were two or three different ways we can describe what's happening here. And what we do, we have to interpret this information into the form of an equation and then make sure the equation is balanced. So nitrogen 13, that 13 is a mass number, okay? And so it would go in the upper left-hand corner. Now, typically you don't want to leave the isotopic notation like this. We want to look at the periodic table, determine the atomic number, and the atomic number for nitrogen is 7, okay? So it gives you the complete story of that particular isotope, atomic number and mass number. And then these are all like what we call first-order reactions. There's only one reactant. And this thing is going to disintegrate into that type of radiation, the positron emitter. Remember, the positron has the same mass as the electron, just as a positive charge. So it has this notation. And then when that type of radiation gets kicked off, then a new isotope is formed. Okay? And so what we're going to do is we're going to use these numbers, top and bottom, the mass number and atomic numbers, to figure out what this new isotope is. And we're just doing math such as, like what number plus 0 equals 13? Well, it's 13. And on the bottom end, what number plus 1 equals 7? Well, the atomic number on new isotope must be 6. 6 plus 1 equals 7. And then if we look at the periodic table, and you may already know this, the atomic number for the element that has the atomic number 6 is carbon. And that's it. And we do this for any type of nuclear equation. Down here, polonium. Polonium-218. So polonium has the symbol of PO with a mass number of 118. If we look at our periodic table, its atomic number is 84. And it tells us that it disintegrates to an alpha particle. I said alpha particle was a helium nucleus, so it's 2 protons and 2 neutrons. So 2 plus 2 gives you 4 for the mass number. And then we do the same thing as before. Bottom numbers and top numbers need to add together to equal both sides. So this has to be 82. 82 plus 2 equals 84. That is associated with lead on the periodic table. And then finally, the atomic number here, mass number needs to be 214. Plus 4 equals a 218. And then to answer this question, I just went ahead and typed in the main points. I just want to talk about a few bits and pieces here. Like, for example, the first two there, they are the ones that are using what we call ionizing radiation. So CT scan, PET scan, both of these uses radiation that's dangerous for you. Gamma ray for the PET scan, as well as the positron emitter, and then X-rays in the CT scan. Whereas the MRI, it's non-ionizing radiation in the form of the radio frequency there. Radio frequency is very low energy, very long wavelength. They are not dangerous to you like a gamma ray or X-ray. And then finally, just an additional little comment about the PET scan. So the patient would ingest something that is a positron emitter, but what's actually detected are gamma rays that's coming out of the patient. So let's just look at that reaction real quick. So first off, what's the positron symbol? Well, we have that. And then what we have to realize is that as soon as that positron is emitted from that drug, wherever it collects in the body, it's going to annihilate itself through a collision of an electron, which there's plenty of electrons in matter. And when that occurs, well, 2 gamma rays are going to be produced. And those 2 gamma rays are what actually detected by the instrument to monitor, where that drug is in the body. That's it. Thanks.